Chapter 13, Buckling of Columns, example number 3. So in this example, we want to study the effect of a buckling on a column provided like uh, figure below. So an aluminum column mhm, with a length of L and a rectangular cross section has a fixed end at B and is restricted as below at A. So that's how it's restricted at the top. Determine the ratio of A over B width to the height of the column itself in order to have the most efficient design against buckling. In part A and in part B, design the most efficient section. So we are solving the problem in a parametric format at part A and then replace it with a numeric value at B. Mhm. So if the parameters are the length of 20 inches, modulus of velocity of 10.1 times 10 to 6 psi, force of 5 kilopounds, and factor of safety of 2.5. So let's start the problem. So by most efficient design in buckling, it means buckling in both directions should be equal to each other. Mhm. That's how we can define a most effective design which in both direction in terms of buckling it is identical. The column is identical in terms of each uh, axis of buckling. So let's consider the buckling in xy plane. So this is xy plane. Mhm. And in that plane, the axis of revolving is z. So in that terms, if you can look at the rotation about or revolution about z-axis, you can easily see that it is topward at the top, acts like a pin. Mhm. So it just you can rotate, but you cannot move in either sides. But there is a little gap here that you can have an angle of rotation there. And at B, it's a fixed one. So if a column is fixed and pin at one end and pin at the other, equivalent L is 7 point L, if you remember from buckling derivation equation. And at the same time, IZ is 112. So a if we calculate IZ, that's a 112 b times a cube. That's how Z goes through this thickness. That's IZ. Mhm. That's revolution about axis Z. And at the same time, we do know P critical in this situation, it's pi squared times E times IZ over effective length square. Mhm. At the same time, buckling in XZ uh, plane, this is X, this is Z. So in that terms, we need to have a revolution about y-axis to be in a buckling in X Z. So that's a buckling, a revolution about y-axis. You can easily see in that term, it just changed to having again a fixed support at B, and this time it's like acts like a free end. So in that terms, we do know if we have a column, one end is fixed, the other is free. LE is 2, effective length is 2 of original length. So that's a 2L. Mhm. And at the same time, in xz plane, that's Iy. And Iy, if it just simply goes through, that's Iy. It just cuts b, so that's a 112 a times b cubed. So if we know this situation, it just gives us critical force at the scenario 2. It's pi squared times modulus of elasticity, this time times Iy, and effective length in that direction, which is 2L. Mhm. And if you remember, the most efficient design is where the two buckling is the same, identical to each other. So it means their buckling force should be identical to each other. If you do that for both sides, it just cancel out the constant and it just says Iz, it's a 112b times a cubed and 112a times b cubed Iy. And if you just simplify them, you can reach to just a a squared and b squared. And at denominator, it's effective length for scenario 1, which one end is fixed and the other is pinned, is 70% of L, and when one end is free and the other is fixed, that's 200 of L, 2L and 0.7 L. If these two are equal to each other, it just gives us A over V in parentheses squared is a 7 point squared over 4, and that gives us a ratio of A over B is 0.35, which we're looking for a ratio for A over B. A is the thickness over the width of the column. So that's our parametric solution. Let's put it in part B in a numeric value to see how that works. So design for a given data. Mhm. If factor of safety is 2.5 and force is 5 kilopounds, it just gives us a P critical is equal to 12.5 kilopounds. Mhm. And if A from the parametric section, part A is equal to 0.35 times B, area is A times B, and it just gives a 0.35 B squared. At the same time, sigma critical stress is just force over area. So we do have our force, which is 1200, 12,500 pounds over the area. Mhm. And if the length is 20 inches, the length of the column, and sigma critical formula from Euler's buckling equation is provided as below. So let's what we need to do here. So buckling, for example, in XZ plane, LE is a twice of original length, and a slenderness of the column. You can go by any direction of buckling because both of them are identical and equal to each other, so it doesn't matter. But be careful if you go for XZ plane, you have to go with the appropriate length for that and appropriate moment of inertia. So that's 2L and Iy. So a slenderness of our column in this direction is just a 2L, which is, and from our mm, effective length over R, which is the equation of R is I over area. So this is our area and this is our Iy. Mhm. That's our Ry because that's we're calculating our Iy. Mhm. And if you do the math, it just gives you 2L over B over square root of 12 and sigma critical likewise It's just P critical over A, which is equal to, this is from a strength point of view, this is about buckling point of view. They are identical to each other. They should be equal to each other. And by having a length of a 20 inches and modulus of elasticity, so we can have a L effective length over radius of gyration, which is a 2L over a B over 12, uh, square root of 12. That's a equal to 138.6 over B. That's just the replacement of numeric value. And then sigma critical is just a force over the area. They should be equal to each other. So that's a, we just replace this part from down. That's LE over L squared. Mhm. And this is pi squared times E, which we replace the numeric value. And if you do so, it just gives us a dimension of B equal to 1.6 inch and A is 35 point B times B, which is 0.567 inches. And the interesting part is sigma critical is P critical over A, which is again 12,500 pounds over the area. And if you do the mass, it just double checking the problem. That gives you a sigma critical of 13.6 kilopound square inches. And if you go to US customary table for a normal stress in US customary unit for any alloy of aluminum, mhm, it just gives you the range of them. So 13.6 is definitely our sigma critical, is smaller than all of the aluminum alloys. So our design is acceptable in terms of a critical stress in buckling. Thank you.